Okay, good. Hi guys, so my name is Esteban. Some of you might know me under my username ZeroTestic. I work at Hidden Layer as a security researcher since like 7 or 8 months now. Today I will present you some of the stuff I do there, and mainly how to find bugs in ML frameworks at scale, and more generally automating vulnerability discovery. So one of the things is ML frameworks are huge. If you take a look at Keras, PyTorch, or TensorFlow, just to name those, they have over thousands of stars, forks, and all of that. So any vuln in there that maybe by loading a model is found, the impact is huge because it would impact a lot of application, either in research but also in production. Because lately a lot of companies start doing AI stuff. So the problem with that is that we simply cannot keep up with the amount of updates being done to these frameworks. If you take a look at TensorFlow, there's a little over 4 million lines of code and around 184,000 commits, and a little under like 4,000 contributors. So it's just a lot, and this is TensorFlow alone. Imagine that, but like around 100 repos to just get the big ones. A team simply cannot keep up. If you take a look right now, you'll see maybe like 20 commits in just today. And if you look yesterday, you'll see maybe like 30, 40, 50 commits. Even if you have a big team and people that are senior, that are used to do it, they just can't keep up with the total amount and all the updates, the deprecation, the new API, the new everything. And so that's where the solution to that is code property graphs, or only part of the solution. It's basically generating a unified graph representation. So this thing, I'll go over it later. It's a bit difficult to see. It's basically a combination of AST, so abstract syntax tree, control flow graph, and program dependence graph. Why these three things combined in one? Because it captures both the syntax, the control flow, and the data dependencies in one structure. It also allows us to do automated and precise vulnerability detection for a very simple reason. Graphs exist since like a long time ago, and we have research, we have documentation on them, we have papers, blogs that talk about them, how to work them, how to use them, how to analyze them. It's something that we all know and can also easily visualize. And what's nice is that graphs are easy to automate on. Any computer that's just installed, any user that's installed NetworkX on Python can play with graphs. So what are AST, CFG, and or PDF? It's supposed to be PDG. So abstract syntax tree represents a code as a code structure as a tree. So here, for example, I don't know if you can see what at the end, but you could represent an assignment. So A equals something as a branch. So here is an assignment, and you can tell it assigns variable A to something, and that something is an operation, a binary operation, which is minus a subtraction. And then you can look that it's subtracting variable A from variable B from a variable A. So you can tell it does A equal A minus B. And you can do that on a whole code base. So it's used in compilers and interpreters, linters. And so if you take a look at linters, for example, those squiggly line is thanks to linters. And so thanks to AST, because they can tell not linters, yeah, they can tell that you added one too much. And so they come and tell you, hey, you should fix this. If you take a look at this one, the formatters, this is what you do. This is ugly, don't do this. And when you run black, in Python at least, it will give you something cleaner. And it's, again, thanks to AST. That is not just AST, but mainly that. You can also use it for static analyzers. So you can look for kind of anything you want. In our case, we will be looking for buttons, but there's much more use cases than just that. And so, yeah, if you take a look at linters, for example, Flake8 and PyLint uses AST. Oops. For control for graph, it represents the execution path in a program. So nodes are basic blocks. This would be a node and a basic block. And I'll show you a bit after exactly what a basic block is. And the edge show possible jumps. So branches, loops, function calls. Here we can see it's an edge, it's a function call to fib. If you take a look here again, this is a function call. This is all edges. And it allows you to see path. So, for example, you can see there is a loop here, and you can tell it's a loop because it goes down, and then the successor is the node that's above it. And so you can tell that's a loop. And here you can tell it goes down until. CFG is used in compiler and analyzer. Yeah. So one of the things is, if we take this program, which does a weird sum, if you looked at it in a CFG, it would look something like this. So you can see there's the beginning where you start at 0, and then there is your for loop here. Then if you're still in the loop, you take the true path, so you go yes. If you are not in the loop, so if you're not in the range anymore, you take the no path, which is return total. And then you can go in and see, okay, well, if you do yes, what does it do? It does I modulo 2 here, and then it's an if condition. So there's two branches again, the true condition that goes in and the false condition that goes in the else. And so this is what it will look like. It's used in a lot of things, and notably in static analyzers to tell things like branch. So if any one of you ever used PyTest, you might have had HTML reports. You can see here, for example, they say branches because it found 4 branches in our program. And you can tell there is 4 because you can see 1 here for the no, 1 here for the yes, that makes 2, and then 1 for the false, and 1 for the true, and 1 for the false, that makes 4. It does a bit of other things, but notably it uses CFGs. There's also in the compilers. So if any of you have ever used IDA, Ghidra, Binja, you'll have seen something like this. This is a basic block. This is 1, this is 1, this is 1. A basic block is a group of instruction that is linear. It doesn't have false or true branches. It doesn't have loops. It doesn't have anything. And so here you can see there is an if condition, and there is a false branch, which is the red line, and there is a true branch, which is the green that goes into the next check. Oops. And finally, program dependence graph. It's a bit too big to show, but basically it represents data and control dependencies in a program. So it allows you to see how values and data flows in which condition and how. Is there like a condition, a check? Where does it come from? Where does it go? And so, for example, if you had a program that defined X in line 1 and it's used in line 5, you could tell the def use chain. So definition would be line 1 and use would be line 5. Oops. It's used in a lot of things, again, compiler and optimizer, but static analysis, program slicing, etc., etc. If you take an example that might talk a bit more to you guys, if you take this code, we can see there is some input that comes from someone that goes in a run. That's checked if it's 0, it's length. So if there is nothing, it just returns. Otherwise, it inputs it into sanitize and also CMD. Sanitize will take it, does some sanitizing, and then execute your system. If we look at what it actually looks like somewhat in a PDG, it would be the source, so your input, that has a dependence on the sanitize call. That also has then a dependence on the assignment to CMD that ends up in the sink, which is OS.system. And OS.system, the sink, has a control dependence, which is the check on the length name. So you can tell here, oh yeah, name also depends on is it size 0 or not. So you were able with just that to tell, okay, well, my flow is, it comes from user inputs, it goes into OS.system, and it checks if len is 0. There is technically also in sanitize, it should also follow, but for clarity, I just didn't add it to the graph. That might have been a bit lot for those that aren't necessarily used to graphs and stuff, but that's okay. We can. So yeah, basically AST shows how code is structured, CFG is how the code flows, and PDG is how the code depends. So syntax and all. Together, what they do is they allow us to have compilers, linters, IDs, security tools, and so many other things. It also allows us to have optimization as well as bug finding, what I will go into, and refactoring and stuff. At the end, what it really does is it allows us to reason about a program. So when we are given code or if it's binary, we can transform it to an IR, an intermediate representation. Instead of having to manually go through all it and think and remember stuff and all, your computer and your program can do it for you by reasoning on a graph. So what makes a good CPG? Well, kind of a lot of things. Obviously, the node and edge must carry attributes. So nodes would carry things like context, the types, the file inline info, etc. And the edges would also carry attributes. Obviously, it needs to have the AC, the CFG, the PDG. Then what you need to add to properly reason about the program is overlays, so call graph, data flows, and also method, class, and type declaration. So just because you think of one single graph for the program doesn't mean it's actually one single one. For example, if you end up calling some function, let's say run, you will have a separate graph for the run function. That's separate, but it gets called, so it's jumping between graphs. And yeah, the edge types also will have ASTchar, CFG successor, data dependency, and all that. So there are tools that already do it. I didn't come up with it. There's Yarn that some of you might know. It's some very cool tool. It's also very mature. It's supports plugin. It has its own query language. There's Fraunhofer, I don't know how to pronounce it, CPG, which supports multi-languages. It's mainly used in either industrial or academic settings, so you wouldn't see people actually use it in their open source program. At least I haven't seen it. There is lately a few newer things like LMX CPG, where they combine CPG and LLMs to try and focus a bit more and get better results and triage. And there is some research that has been out, which is enhancing software vulnerability detection using CPGs, those neural networks. And it basically shows the advantage of the CPG and then adding on top some ML. So why did we make our own instead of using those? Well, there are a few reasons. Mainly that it's too heavy and complex for us. We have needs that aren't as big and as general purpose as what others could have. So yeah, things like that. It's also very overkill for our needs because, like I said, most are very focused on general purpose, and we only need to find bugs and maybe a few data, but that's about it. Where things like Yarn allow you to do kind of everything, basically. You can query for whatever you want at the end. And yeah, basically, sometimes we have specific use cases where because we are an AI company, we will want to see how users and developers use certain API or certain libraries, and being able to just use that tool to quickly query it and know on a large scale is nice. because there are tools like, Yarn or Fraunhofer. It's just too much of a hassle to set it up for the project. You need to install it very complex. You need to point it properly, load it, let it build the CPG and stuff. It's just not easy for us. Also, for the agility and automation, it's easy for us to just be able to put it in a CI, to drop it on some project at scale. And yeah, maintainability is, we are a small team. We don't want to have a bug and then be like, oh, we need to make an issue to Yarn and have to wait or make our own fixes or whatever. And we know the code base, it's also much, much smaller because it just makes sense. And yeah. Oops. There is also some issues. Scaling CPGs, the richer your graph is, the more detail you have. And that makes sense because you also get a better precision. The issue is, well, it requires more memory, and anytime you're going to make queries, it's going to be slower because it needs to go through your whole graph. Also, graph size can be very, very big. If you used it on TensorFlow, the projects are like 4 million lines of code. There's many lines you just don't care about. There is also the need for pruning, slicing, and abstracting all the irrelevant nodes, the focus on control data flow that you might not care about. Maybe in your case, you will target a code base and you know that the attacker will never have control of the environment, which is often the case. Well, you just don't care about those parts, so you should prune them. There is also handling dynamic and or generated code. Anytime you do imports on libraries, every time you generate code at runtime, or things like that, you can do a best effort, but you can't generally handle it all, as far as I know. And of course, multi-language or mixed sources. So sometimes you'll have code bases that uses C and then Python or Rust or whatever. If your CPG and so your tool doesn't handle them all, well, you will miss some data. That might be fine for you, but it's just something you need to know. And yeah, CPGs are very good, they're very useful, but they don't solve everything, like I said. The issue is you might get a lot of false positives, and this ends up being a problem of soundness versus completeness. So you will need to choose between it being sound, and so any results you get, you are confident they are true positives, versus being complete, where all your results and all the bugs are present in the reports, but a lot might be false positive. And so you need to be able to have some balance between the two, where you must accept that some results might be false positive, or you might miss some bugs. And that's what companies do. If you use any professional detection tool that finds bugs and stuff in your company, you'll notice you have a few false positives, maybe a lot if you use a tool that's not as good. And they have to decide between finding it all or not and having to let the customers triage the reports. There is also, well, like I said, missing context. So any runtime states, external input sanitization, so configuration, environment, these are all things you cannot really model unless you do it very, very specifically for one program. And the dynamic behavior. So like I said, again, all the reflection, the code generation, runtime module loading, depends on how you do, but you will miss a lot of it. Thankfully, most code bases don't do it too much. They are somewhat okay. Yeah, obviously, if it uses binaries or compiled dependencies, unless you have something for it, it's not gonna be resolved. And maintenance burden. The tool will change a lot. Across version, the assumption you had for one detection might be broken in the next version, so you need to keep it updated and keep an eye for things. But that lowers the burden a lot on the team. And so when you have all that you know all of those things, well, you can do very easily. You build your ST CFG you make it a CPG, and then you can query, okay, well, where is my entry point? This can be known functions like input in Python, or endpoint API that you can detect with Flask or Fast API or whatever. And then you can follow its track and say, oh, well, does it end up in this serialization code, and does my inputs end up in an execution sink? Or you could do the opposite too and say, well, what from my execution sink goes and backtrack it all. There is two ways to do it, because sometimes you will have a lot of entry points but very few sinks, and it doesn't make sense to check all the entry points when you could check just the sinks and go back from there. And the other way is correct too. If there is only a few entry points at a lot of sinks, it doesn't make too much sense to check all the sinks when you could just check all the entry points. So what you usually do is try to make some smart mix of the two to avoid missing stuff. And then you can rank them based on threat level. So you might be able to say from just the CPG already and give some confidence to your finding. Like, okay, well, this one is maybe from the API, but it's weird because there is some headers and checks from this function that I couldn't tell or something, whatever. So you just rank them and then you scale. So that's what we did. We repeated it across frameworks. We scan a lot of tools. I think it's like 150 daily. And then there are a few more that are less often updated or less critical that we scan around weekly. So cool. I explained you all of this, but what does it look like in practice? This is one of the bugs I found that has been disclosed in early August. It's fixed now, but it's a RCE in Keras. And so just loading a model, even with safe mode equal true, would lead to an RCE with the payload. It has been very, very quickly found and so very quickly patched. You can see at the bottom there is only 2 minor patches versions that have been affected. So most production settings shouldn't have been affected by it, or they could have just updated to the patch version. So I built a little frontend for the tool because it's just easier for us to triage all the reports. You can see here it reports a torch load. So torch load was vulnerable by default a while ago to pickle deserialization. So you could input it some pickle data, and if it was a malicious data, it would get RC because it gets executed. They then added a patch which is weight only. And so when you say weight only equal true, it only gets the weight. And so even if you pass its pickle data, it won't get run because it doesn't get it. And so it's also a default value. But here, for some reason, they set it to false. And so you can RC it. So after a little bit of backtracking and figure out, you can just do a little setup and then call the function. And when you do, you can see it print spawned, and which is the payload that's set here. So cool, an RCE. But who uses that class? Because this is kind of a weird setup. Honestly, I wouldn't personally see anyone actually use it like that. Well, no one uses it. At least on GitHub public, it's just forks basically, and a few documentation. That's annoying. So how do we escalate that? We can get RCE, but it's a weird setting that no one really uses. There are a few things you should know on the Keras formal model. Keras is basically just a zip file with a config.json, which contains things like layers, hyperparameter, training setups, a few names, and some data that isn't always there. It's optional data. Then you have your weight, which is probably one of the most important parts, that has basically all the parameters. And then you have some metadata that's used from the framework backend, the Keras version, and all. One of the most important thing is config.json. If you look in Keras before, there already was a lot of attacks done on it. So modular codes is basically, there is something called Lambda, which will run code when it's used. So obviously you could just set a Lambda with bad code and it would run. This has been fixed with safe mode equal true, so you can't do it anymore. Keras downgrade attack is, there is an older version of Keras called H5, and you could downgrade it halfway through and get code execution again. There's also the code execute via config model. You could just arbitrarily call functions in the config, and there are a lot more. So yeah, we could just find a bug in there too and exploit it, right? Well, yes, but there are a lot of functions and fixes since then. So obviously safe mode. They also limit function calls to only be function in classes that have the Keras export header, and there's only 8 of them, so that's not a lot. And you have little control over how function classes, the function classes, yeah, are called. So yeah, there's more even fixes, so it's painful, but maybe we can find something. It calls functions. If you look in the deserialization, you can see at some point it retrieves a class or the function you give it. And it's attributed CLS. And then they use CLS and they call from config with some config you can give it. Wait, it calls from config. That was our vulnerable function. So we should be able to arbitrarily call it, right? Yes, because it's also exported. So this was very lucky because they used both the function that's vuln and they exported by default. So what now? We can just inject config.json with our class, craft the model, something, and then profit. Well, it's not that easy. Pickle is raw bytes, and we are giving JSON data. If you try in Python, it's going to give some errors. You can see here, it takes the bytes as is, and it takes it from our config. So what, are we stuck? Because we can't do anything at this point. Well, it turns out the Keras team realized this was a mistake and it broke some of their components. So they fixed it. And they used base64, and base64 goes very well in JSON. So now what we can do is base64 encode our pickle data and give it to the module and call the function. So we can do a little of pickle and JSON. This is enough to run just the RC. It would crash and tell you more model is invalid, but it would RCE. And so what you need to do is give the class name, which is torch module wrapper, and the module, so where it comes from. Then the config is what you care about. The main part of it is obviously the module, which is what's used in the payload. If you take a look here, you can see it's config module. And the name. The name doesn't really matter, but it has to be here. And the D type, same. It doesn't really matter to the exploit, but it has to be here to load properly. And then you can just show it in a JSON. Add the weight. You can do dummy weight. It doesn't really even need to have weights. You can give nothing and it will work. And so when you run it, it works. And so from that, we can load any model we want. Well, any model we can load in Keras could give us an RCE. And so any production services that uses the very vulnerable version is vulnerable to RCE if you control the model given to it. That was a lot between learning what CPG is and AST and all, and then obviously poking an RCE. What do we learn a lot? Well, we learn a lot from it. AI/ML is still a very new field. That's actually kind of a lie. It exists since a while, but it's only been picked up since recently. I think you all know what I mean by that. It grows fast, very fast. You've seen it. There's like commits every day. There's huge code bases. There's new tools every day that are released. I think anyone who keeps up a bit on Twitter, internet, Discord, anything, will see new tools basically every day. Automation is essential. You cannot find bugs at such a scale with just humans, unless you have like infinite money and infinite everything, basically. Safe defaults aren't always safe. I just proved it. Just because you set safe equal true doesn't mean I cannot pawn you. And so that's everything, your models, your source, your file formats, your frameworks, your everything. And yeah, that was it. Thanks. If you have any questions. Yeah.
So you said that you created your own creation tool, right?
Yeah.
So what were the design decisions that you decided to go with? For example, did you add a lot of data to the graph, or was it more performance-based?
So the thing is, because I am a researcher, I'm okay with having false positives and stuff like that, because I can just spend my time triaging. So I added more data, because since it's scanned daily anyway, whether it takes 2 minutes or 5, personally doesn't really impact me. So I'm fine with having more data to try and have less false positive, and then make queries that are more complete but less sound, and then I have a few false positives that I can just triage out. Yeah. So yeah. If you have any other questions, you can find me on the Twitter I said at the very beginning. Otherwise, I am on Discord. You have probably my username here. I have LinkedIn also if you want to. And yeah, that was it. Thanks for listening, guys.